This is lesson 7-5, exponential models relating to percent. When we talk about models that are exponential when it involves percent, it relates itself to a lot of real world examples that deal with increasing and decreasing by the same constant percent rate. From those numbers that come from certain studies or any type of money growth from an account, we can then create exponential functions from those situations. Your steps to these problems are to identify your initial amount. If whatever you're talking about is growing, you want to take the percentage, change it to a decimal, and add it to 1 to make the growth factor. If they're decreasing, you'll subtract the percentage as a decimal from 1 and make that into the decay factor. This is extremely similar to our last lesson except this time we are making it a decimal and then subtracting from 1 as opposed to subtracting it from 100%. Keep in mind several things as we move forward in this lesson: that our domain is the x values, typically the x values. It's the independent values that are used in any situation. The range is dependent upon the domain. It's typically your y values or your f of x values if you're in function notation. And anytime we're asked for the domain or range, we can describe it using inequality or interval notation. Usually it's your choice, but please make sure that you know both in case they are asking for a specific way to display it. Here's a growing example. So we have a population of fruit flies that's growing at a constant rate of 6% per hour. The population that starts at time equal to 0 with 28 flies. Based on the information just said to you, find a formula that models the population P as a function of time in hours T. And then from there, find the value of P of 24. Now keep in mind, you must use P and T as your variables because it was stated so in the problem. Pause the video at this point to give yourself a chance to try it on your own. So for this particular situation, I'm going to be using, again, my standard form of an exponential function, which is a times b to the x. Now, the one thing I should have done here, and I will do right now, is as I just said to you before, we want to make sure that we are using the variables that they gave us. So I mistakenly put x here. I should be putting t here for that. A and B don't change because A is going to be your initial amount and B is going to be your, in this case, growth factor. So for this, P is going to be equal to 28, which is my initial value, times 1.06, that's my growth factor in this situation, all raised to the 24 power, because again, we're talking about time. And we want the value of P of 24. We'll evaluate that function, and we get 113.37. It's a long irrational number. So at this point, I need to consider what my problem says. And it says that we're talking about fruit flies. Fruit flies have to be in whole numbers. So I'm going to truncate the decimal, cut it off, and my conclusion statement here will be the population will be 113 flies. So now, in continuing this example, we want to state the range of the function over the interval 0 to 24 for time. Then we want to graph the function over the same interval. Pause the video at this point to give yourself a chance to try it on your own. So, when time is 0, P is 28. When time is 24, P is 113. So our range is going from 28 included to 113 included. Now, if you were going to do that in interval notation, it would be 28, comma, 113, both with staple brackets. Now, as far as doing the graph, I'm going to go up by twos, and I'm going to go up by tens on the p-axis. My first point is, again, 0.28. Time being 0, the population being 28. That's going to be directly below the 30. Again, you don't have to be exact. The second point will be 24 and 113, because at 24 hours, the population of the fruit flies was 113. So I'm going to take my t-axis out a little bit so I don't make a mistake. And I'll also take my p-axis up a little bit. And so at 24, 113, we're looking at just above the 110 mark. Now, this needs to be connected in an exponential curve. The key part is this. It only wants me to graph the function over this interval. This is not going to be a continuous function when it tells me to graph it only over the interval. So, when I connect the dots in an exponential curve, I'm going to stop at that top dot. There is no arrowhead, and there is no continuous function going through the graph. When a graph tells you to only graph on an interval, you must start at the starting point and you end at the finishing point. You can label it and I should be labeling this with P and T on that graph. If you're having any issues with any portion of this lesson, please make sure you're emailing me or consulting me in class.